Okay.
All right. Awesome. So for the second speaker of today's session, I'm happy to introduce Professor Georgina Hall. Georgina is an assistant professor of decision sciences at INSEAD in France, where her research focuses on convex relaxations for NP-hard problems, particularly polynomial optimization and problems on graphs. Before joining INSEAD, Georgina was a postdoc at INRIA, and she completed her PhD in operations research and financial engineering at Princeton. She's received a number of awards for her work, including the 2018 Informs Optimization Society Young Researchers Prize Award and the 2020 Information Theory Society Paper Award, as well as having been a finalist for the Tucker Prize, a very prestigious one. So today she's going to tell us about something which, when I read the title, I thought that's an applied talk. And then when I read the abstract, I realized there's a lot more besides that. So Georgina, please go ahead.
Thank you. Thank you very much. I'm really excited to be here, actually. So this talk is about an application really of, these techniques that exist in integer programming to sustainability. So it's really cool to be able to present to this community. So the title of my talk is Traceability Technology Adoption in Supply Chain Networks, and it's joint work with two fantastic collaborators, Philip Bletch and Andre Carmon. So let me tell you a little bit about the application we're considering. So the application we're considering is in traceability. So I'm sure you're familiar with the notion of traceability. It's basically you want to know where your products come from. So where do they originate from? How were they processed until they get to you? And so there are major positive points about traceability for both the person who sells the product and the consumer. So for the person who's actually, producing that product, it makes things like recalls easier if there's a health problem, and it also enables the firm that produces the product to say, for example, that this product is produced in a way that fits with its environmental or ethical principles. For the consumer, on the other hand, consumers like more and more to know where their food comes from or where their product comes from. So there's an increased demand for traceable products. So traceability is really something that is quite key and that is quite, that has a lot of money to be made in it. So in line with this, there are many new initiatives that have been developed. So these initiatives, what they want to do is they have a certain traceability technology. So, some kind of technology that enables the products to be traceable. So this is just a subsection that you see here. So all these different companies, they propose their own traceability technology. And each one of these companies has one goal, which is to become the industry standard. So they all want to be, the technology that's used to make products traceable. And so one way that they do this is they give freebies out to a set of early adopters. So they give their technology for free to certain companies. And they hope that these early adopters are basically going to pull other firms in such a way that then this technology becomes the standard. So the question that I'm going to be trying to answer throughout this talk is, what's the smallest set of early adopters? So I'm also going to refer to that as the seed set. So what's the smallest seed set that these companies should target to ensure that their technology gets, diffused globally across the whole of the industry? So before I can even tackle this question, you need to have a notion of how traceability technology actually diffuses in a supply chain network. So how, if one person adopts this technology, how likely is it that other people will adopt this technology? So that's what I'm going to do first. I'm going to tell you a little bit about how we model traceability technology diffusion in this case. So first off, why don't we use a traditional diffusion model? So there are a lot of diffusion models out there, right? But the downside of these existing diffusion models is that they always have this kind of an assumption in them, which is an agent in my network, right, is going to adopt if its neighbors or a fraction of its neighbors have adopted. Now, in traceability technologies, that doesn't make a lot of sense. So let me give you a very concrete example. So here we have a supply chain that we're considering. So we have the farmer, the distributor, the producer, the wholesaler, all the way up to the retailer. And if I focus here, so the firms that you have that are colored, right? So the distributor, the wholesaler, and the retailer, they've adopted the technology. So they have this ability to make their products traceable. Now, two people in the supply chain have not adopted, right? So that's the farmer and the producer. So let's focus on the producer. So the producer here has not adopted. And when the producer decides whether to adopt this traceability technology or not, it doesn't really look around it, right? So if it does look around, it sees that the distributor has adopted and the wholesaler has adopted. In traditional diffusion models, it would mean that the producer would adopt. Now, for traceability technologies, that's not really how the producer would think. The producer would look at the whole supply chain and see that the farmer hasn't adopted this traceability technology. So if the producer adopts this technology, well, the product will still not be traceable. So for example, if this is beef, right, that's going down the supply chain, even if the producer adopts, the beef is still not traceable. We don't know where it comes from because we don't know where the farmer went and got the beef. So essentially, there's not much value for the producer here in adopting the technology. So this is the difference with existing diffusion models. So instead, right, what we need to have is a model that encodes the following idea. The producer or anybody in the supply chain will only get the full benefits of traceability if everybody in that supply chain adopts. Okay, so that's the key difference with existing diffusion models. So in this case, for example, right, the producer would have some incentive to adopt because everybody has adopted. If the producer adopts, then he or she makes the product fully traceable, and then suddenly there's, value in making that product traceable. So in fact, what's going to happen is the producer is going to look around and it's going to see that there's a certain benefit from adopting this product traceable, and if that benefit exceeds the cost, then it's good to go. Right, so in this example, where we only have one supply chain, it looks like everybody, so 4 out of 5 people have to be in the supply chain, in the seed set, right, for adoption across the supply chain. So diffusion doesn't seem to bring much here. So in fact, diffusion only really kicks in when we have a network of supply chains. So when we're looking at many different supply chains that are overlapped and intermingled. So that's going to be what I'm going to discuss next. Questions so far? Okay, so this is our diffusion model more specifically. So in this graph, I'm representing firms that are in the supply chain network by nodes. So I have 9 firms here, 9 firms total. And then I'm going to represent a supply chain. So that's people who collaborate to make one product. So I'm going to represent a supply chain here by these hyper edges that you see. So there's 4 hyper edges in the graph. There's a red one, a blue one, a gray one, and a black one. And to each supply chain, there's a benefit that the firms in the supply chain get when that supply chain becomes traceable. And it's given here. So for example, if suddenly this red supply chain becomes traceable, well, every single node in the supply chain is going to get a benefit of $2, okay? So the benefits are defined per supply chain. So when a supply chain becomes traceable, the nodes in that supply chain get this benefit. But then there's also a cost of adoption for each company in the supply chain. So for example, for node 5, it will cost them $2 to actually get this technology. Right. So we're going to start off this diffusion process with some nodes that already have the technology. They're the people to whom I've given my technology for free. So these are the nodes that you see that are colored. So 1, 2, 3, 4, and 7. So these 5 nodes already have the technology. And the question is, who else in this graph might adopt? So if we take a look supply chain by supply chain, in the red supply chain, 2 nodes are missing the technology, so they don't have much of an incentive to get that technology. In the blue supply chain, there are 2 of them as well, so same thing. They're not very driven to actually adopt this technology. But if we go to the black supply chain here, this node 9, well, if node 9 adopts, then suddenly the full supply chain becomes traceable. So there's an incentive for node 9 to adopt, because if node 9 adopts, it gets $3 coming from making the supply chain traceable. So it will get $3. Given that the cost of adoption for this company is $3, the benefit is greater or equal to the cost. So node 9 would join, right? So node 9 joins. Then if we look at this green supply chain, there's only node 5 missing to make this supply chain feasible. So node 5 starts considering whether to adopt or not. So 5 does decide to adopt the technology, to join the people who have the technology, because the cost to node 5 is 2 versus the benefit that they will get, which is 5. So that makes sense to them. So now we have 1, 2, 3, 4, 5, 7, and 9 in the supply chain. We can move on to node 6, which again, if node 6 joins, then suddenly the red supply chain becomes traceable, right? So that they will get benefits. Now let's look at how much benefit node 6 will get. Node 6 will get $2, but it costs them $3 to join. So node 6 will not join, and diffusion will stop there. Is this clear? So this is our diffusion model that we're using here. And so this tells us basically with an initial seed set, where are we going?
Quick question. If the seed set is such that there does not exist any supply chain for which one extra node joining gives benefits, then that's the fixed point, then nothing happens.
Nothing happens.
Okay, so there's like a minimum size and structure that
Exactly.
needs to be
So
satisfied.
So at least, right, if your size of your supply chains is say K, right, then you need at least K minus 1 nodes to get started. That's the bare minimum that you need. Absolutely.
Okay, cool.
Other questions for me? Okay. So this is the most simple version that we have, right? We have a more general version in the paper. I'm just presenting something that's easy to talk about. So more generally, what we're able to do is here you see that these supply chains, they all have 4 nodes in them. That doesn't have to be the case. They can be smaller. We can also have benefits of joining the supply chain network that are specific to each firm. So there's many more things we can do, and in particular, the more general version does stuff like encoding power relationships between nodes, because you can imagine in a supply chain network, Walmart, for example, is much more powerful than a small, supplier. So these power relationships we can encode, for example, in our model. So this is our diffusion model. And under this diffusion model, the problem we're interested in solving is the following. So what is the minimum seed set that we need to consider, such that all the nodes in my supply chain network at the end of the day end up adopting following this model? So I'm going to refer to this model as the SCTM problem. So it's really the question I'm interested in from the beginning, which is what is the minimum seed set that will become the industry standard? So that's the MIN-SCTM problem. And unsurprisingly, right, this problem is hard. And it's hard even when there are no thresholds. So there's no question of, who gets the benefit, who gets the cost. As soon as you can adopt, you adopt. So even if I remove this idea of benefit cost analysis, it's still a hard problem. And it's even hard when the size of these supply chains is 3. So essentially, what does the theorem tells us? It tells us that the underlying structure of my supply chain network is really what's conditioning the complexity of the problem here. And in fact, it's even hard to approximate. So, it looks pretty negative at this point in time. So because we know that the structure of the underlying supply chain network is what drives the complexity of the problem, a very natural question to ask is, are there certain structures that make the problem easier? And in a lot of communities, there's this notion of treewidth, right, that has been identified as being a key driver of complexity in many different problems. And so what we're able to show, and I'll give the exact theorem in just a minute, is that MIN-SCTM has a fixed parameter tractable, so an FPT algorithm with parameter treewidth of the supply chain network. So essentially, the supply chain network is a graph, right, a hypergraph. And the treewidth of that hypergraph is what drives the complexity of the problem. So just a quick recap for those of you who are not very familiar with the concept of treewidth. I'm not going to give you the exact definition, but just at a high level, right? As the name seems to indicate, the treewidth of a graph is basically the degree of resemblance to a tree. So the smaller the treewidth, the more it looks like a tree, and the larger the treewidth, the less it does. And what's particularly interesting in our case is that actually real world supply chains, when you look at real world supply chains, they actually have small treewidths. So there's empirical evidence that real world supply chains actually have small treewidth. And so that an algorithm like this is actually quite good to have. So for example, if you take a look at this well-known data set, this Willems data set that has 38 different supply chains in it, And these supply chains are said to be representative of different industries. So that's the paper. If you take a look at the nodes, the number of nodes in this graph, you have a high number of nodes, like around 1,000. But when you look at the tree width, we're going down to, a couple, dozens maybe at most. So there's a real gain to be had by going from, dealing with a problem that has just nodes to a problem that, is parameterized with tree width. So this is the interesting part of this application, is that at the end of the day, an algorithm that leverages tree width is pretty useful in practice. Right, so this is our exact theorem. So the theorem we're able to show is the following. So we're going to assume that the number of tiers k is fixed. M is the number of supply chains, and n is the number of nodes. And so if the supply chain network has this tree width omega, then we can solve this problem exactly in the following time. So 2 to the power of omega. Then we have a maximum of the number of tiers with the costs to the power of omega, and then something polynomial in the number of supply chains, the number of nodes. So that's our result. So just to give you an idea of how we do it. So essentially we reformulate the supply chain network problem. So the problem, the MIN-SCTM problem, we reformulate it as a binary integer program, as Yatharth was mentioning in his talk. So maybe we could use branch and pound in the future. The supply chain network, we're going to first transform it into an auxiliary graph. So we're going to use a different representation of the supply chain network. So this is just a membership graph in some sense. So we add nodes here, 1 node for each supply chain we have. So we have 4 additional nodes here, E blue, E red, E black, E green. And we're going to connect nodes 1 through 9 that we keep to the supply chains they belong to. So it's a membership graph. And then we can write the problem that we had, this problem of finding the smallest seed set over the supply chain in the supply chain network to get the industry to become the industry standard. We can write this as a binary integer program on the auxiliary graph. So what does this problem look like? Let me just give you an intuition as to how it's written. So we have, so this is what it looks like, but I'm going to take you through it line by line. So we have, first off, 3 types of decision variables. So we have the SIs that are here. So they correspond to the question, do I seed firm I or not? So my SIs are going to be in 0, 1. And if I seed firm I, then it's going to be 1. And if I don't, then it's going to be 0. And then we have 2 auxiliary sort of decision variables, the LIJs. And so LIJ is 1 if in this activation process, it's the fact that it's the firm I that's activating the supply chain. So the firm I, by joining, makes the whole supply chain traceable. So that's what LIJ encodes. LJI does the reverse of that. So it says, okay, my supply chain has become active, so we get my firm I to be active there. So this is what these decision variables correspond to. The goal, of course, is to minimize the cost of seeding. And then we have a bunch of constraints. So the first constraint here says a firm is only going to activate via supply chain if the benefit is higher than the cost. So that's what's going to happen here. And then this constraint says that a supply chain is only going to activate from firms if at least k-1 firms have already joined. Here we're saying that you can only activate in one way, right? You can't have both happen at the same time. And the last constraint is a very important one because it precludes auto-activation. So you cannot activate from yourself. So there are no cycles in the activation process. So with this binary integer program, we're able to apply different techniques. So we can rewrite this integer program in such a way that an important concept called the intersection graph has tree width bounded by the tree width as a supply chain network. And then there are ways of rewriting this as a linear program, which has size FPT and which has size which is exponential in the tree width of the supply chain network, but polynomial in other quantities. So yeah, from then onwards, we're leveraging a lot of the literature on the topic. Any questions for me at this point? Otherwise, I'm going to move on to the kind of insights we were able to get.
There is a question from Gonzalo in the chat. He asks, is the problem hard because it has a covering feeling to it? I guess similar to the vertex cover type thing.
So so absolutely. So our reduction is not from vertex cover. Our reduction is from another diffusion model called the linear threshold model, but the linear threshold model itself is shown to be hard via vertex cover. So yeah, it's like a couple of lines, a couple of ranks down from vertex cover. So yeah, that is the intuition.
Okay, great.
Okay. So let me now move on to some managerial insights we were able to get by solving this problem. So there are a couple of questions that interest companies, right, at this point in time. So they want to know, looking at the supply chain network, they want to have a couple of answers on what is, what drives seed set size, for example. So if they have to seed many different companies, then that costs them probably more money. So they're interested more in supply chain networks where you don't have such a high seed set size. And our first conclusion is that Jacquard clustering, which is a definition of clustering that is maybe less classical than what you have in mind as clustering. So the Jacquard clustering is a measure of how similar the neighborhood of a node is to the neighborhood of its neighbors. So there's a lot of neighbors going around here, but let me just give you an example of what has high clustering following Jacquard clustering and what has lower clustering. So on the left-hand side, we have an example of a graph with higher clustering. And on the right-hand side, we have an example of lower clustering. So how do you interpret this? You take a look at the nodes 1 and 3. They share the same supply chain, which is this blue supply chain. Same thing for 2 and 4. So essentially the neighbors, in the sense of this auxiliary graph, so the neighbors here, they share the same neighbors, and 5 does not. But overall, everybody seems to share the same neighbors. This isn't the case here, right? 2 is in supply chain, the blue supply chain, whereas 1 is in both the red and the blue supply chain. So these neighbors don't really share the same neighbors. So that's the intuition behind Jacquard clustering. And what happens is higher clustering seems to lead to a larger seed set. So the higher clustered you are, the larger the seed set you have. So we would tend to go with something that has lower clustering, if that's what, if you're trying to, not spend too much money as a company, then you would want to go with something that has lower Jacquard clustering. So that's our first insight. And then the second insight is what is the structure of the seed set size, of the seed set itself. So what is the structure? And let me tell you a little bit about 2 different nodes that kick in this graph. So we're going to make a difference between what we call helper nodes and starter nodes in diffusion. So helper nodes, we define them as being part of supply chains that only become traceable in later stages of the diffusion. So let me give you an example on the very first graph we had. So you see here, we have 5 different nodes that were in the seed set, right? It was 1, 2, 3, 4, and 7. Now, 2, 4, and 7 led to the immediate activation of 9. So 2, 4, and 7 are what we call starter nodes, because what happens is once they're activated, they lead to immediate activation of a bunch of supply chains, the green supply chain, the black supply chain, the green supply chain. On the other hand, 1 and 3, they intervene much later. So they intervene in order to activate the red and the blue supply chains, but that happens in a future time period. So we refer to 2, 4, and 7 as our starter nodes, and 1 and 3 as our helper nodes. And 1 and 3 the helper nodes play a strategic role, because if you're a company looking to seed a supply chain network, these you have to do at the very beginning, because they jumpstart, they lead to the start of the diffusion process. But 1 and 3, you can wait a bit. So you can wait for the diffusion to happen, and then you go in and specifically target a couple of nodes. So the helper nodes play a very different role to the starter nodes in this diffusion process. And the question we were interested in answering is, how does the ratio of starter to helper change based on the underlying structure of the network? And what we saw is that modularity has an important role in this ratio. So there's a convex relationship basically between modularity and the percentage of start and helper nodes. So this is very well illustrated in this example. So you have different levels of modularity here. So modularity, if you don't know what it is, it's just, how clustered things are. So how connected are our communities, and how not very connected they are across communities. So this is a very highly modular graph because you have two distinct clusters, actually. This is a low modularity graph because everything is very connected across the two clusters. And in the high modularity setting, what happens is you have disconnected components. So you're going to have starter nodes up here, starter nodes down here. In fact, you won't need helper nodes because the starter nodes are going to take care of each one of their component. And there's no need really for diffusion to transfer. So there's no need for helper nodes in this setting. This is different from the intermediate modularity setting, where you have some overlap across the groups in the network. And here the helper nodes, you're going to have starter nodes, say, for example, in this group, and you're going to need one helper node up here that helps transfer the activation to the second set. So here we have a number of helper nodes that goes up. And when we're at low modularity, everything is so connected that you just need to start it in one cluster and watch it just propagate over the second cluster. So in this setting, you have lots of overlap across the groups. The seed set is going to be small anyway, and there's limited need for helper nodes because it's so connected that you don't actually need to help out. It will just propagate as you want it to. So this is where you see this relationship where essentially here you have very few helper nodes, here you have very few helper nodes, but when you're in this intermediate modularity setting, you have many helper nodes. Okay, so let me just wrap up on what I talked about today. So today I considered the application of traceability technology diffusion. So the goal here is, who should I be seeding, right? What's the minimum number of early adopters that I should target so that the technology becomes the industry standard? So to do this, I had to introduce a model for traceability technology diffusion. I showed that the problem is hard to solve and approximate in general. However, there is some hope because there is an FPT algorithm with respect to parameter treewidth of the supply chain network. And what's quite nice is that, experimental evidence seems to suggest that, in fact, real supply chain networks do have small treewidth. So there is something to be gained there. And then once we have this algorithm, we're able to deploy it on different supply chain networks and gain managerial insights as to what the size of the seed set is and what is the structure of that seed set. That's it from me. Thanks very much for listening.
All right. Thank you very much, Georgina. So there is one question. Dawn, do you want to ask it directly? Or do you want me to read it? Okay, so question is, I wonder if the motivation behind SCTM is to find a minimal set in order to maximize network benefits. Hence, we are further down finding structural information, number of nodes, treewidth, which lead to low problem complexity. So the question is about kind of the general approach.
Yeah, so absolutely. So we are absolutely, we're leveraging like more structure. So in diffusion models here, what we're bringing is some kind of additional structure to the underlying graph on which the diffusion is happening. And the specificity here really is that in terms of other diffusion models, right, is this notion of everybody has to be in the same, you have like hyper edges, right? You have groups to which nodes belong to get that benefit. And this isn't only actually something that's interesting for, say, traceability technology, but anything where you have a common set of people who have to work, say, for example, the same tool. Like you could imagine that this being used for like diffusion of, say, overleaf, right, in different in the academic world. So it's not limited to traceability technology. It's a bit broader than that. It's anything where you need many people to join to get some kind of benefit. So I hope that answers your question, Dawn.
All right, great. So we're now going to thank the speakers and have a social breakout session for about 20-25 minutes. So if you would like to ask the speakers questions separately, you may join the sessions, which I'm trying to create